So this brings us nicely to talking about the indefinite integral. The actual definition of an indefinite integral is the set of all antiderivative, that infinite set of antiderivatives that are antiderivatives for the given function. So in other words, the given function is the derivative of the thing we just found. So capital F has the parent has little f as its derivative. So really, when you're looking at an integral, it's absolutely okay to say that this is a derivative, and we're looking for its parent, the thing that has that little f as its derivative, which is why you'll never see this in a textbook, and a lot of math teachers don't like to say it, but I think it's okay to think of this intuitively. It's not technically accurate. There's some complicated math behind it, the reasoning as to why it isn't, but we're not going to get into that. Instead, we're just going to develop a solid intuition for success in future math courses, and that is, yeah, you can, I deliberately didn't use f here, but I used g. So when I look at an integral, you look at the integrand. The thing inside of it is called the integrand. You look at that as the derivative. It is a derivative, and we are trying to find the function that has that as its derivative, which I'm going to informally call the parent, the function that has that as its derivative. So, I don't know, for an example here, we could just far fancier than where we're at yet, but I bet you we could even think this through. So the integral of x squared minus 2x plus 5 dx, and you don't yet know that you can split integrals across things. We're going to cover all that stuff formally here, but just looking at this expression as a derivative, we ask ourselves, what has that as its derivative? Sorry about that. So what expression has x squared as its derivative? Well, x to the third, some flavor of x to the third, but when I take the derivative of x to the third, I'm going to drop down a 3, but there's no 3 up in that integrand, so we're going to have 1/3 here. That way, if I drop down to the 3, that'll reduce away to 1, and I'll be left with just x to the square when I take its derivative. What is derivative of 2x? Well, x squared. Drop down the 2, subtract 1. What has derivative of 5? Well, you just need to tack an x on the end. And then, well, you could also just add any old constant number, and you'll still get that derivative inside. That's it. We start with the derivative, and the integral tells us to look for the function that has that thing as its derivative. That's what an initial value problem is. That's what a lot of differential equations is about. Yeah, so I think while you're not going to see it written this way, I love this intuitive approach for this. So that being said, we just talked a little bit about the power rule in disguise. Let's talk about the power rule. So again, we're working on building an intuition. That integration is the reverse or inverse operation. Again, thinking of differentiation as an operation on a function, we're doing the reverse operation on the derivative and finding the original function. So it's kind of undoing or the reverse of differentiation. As such, all of the differentiation formulas we know will help us to understand a bunch of new integration formulas. Again, we're not memorizing formulas here. We're thinking about the relationship to what we already know. So the differentiation power rule, x to the n, the derivative of that expression is drop the exponent down and then subtract 1. So to reverse that process, yeah, we're going to have the integral has the function inside the integral is the derivative, f prime of x. So x to the n is the derivative. Well, what has the derivative of x to the n? Well, to reverse the process of differentiation, how did we get the exponent? Well, we subtracted 1. So to get the original exponent, we're going to have to add 1 onto it. Now, we don't want, because there's no constant, there's no number out in front of this derivative here in the integrand. So to counteract that, when we take this n plus 1 exponent here, if we were going to take the derivative of this expression, we would drop down the n plus 1. And there's no n plus 1 in here. We don't want 1. So to counteract that, we multiply this by the constant 1 over n plus 1. So it's a little harder to think through, but that is the power rule in reverse for differentiation. We're going to go ahead and check this a few times. So, all right, just recklessly following the formula here, in this case, n equals 2, we would have 1 over 2 plus 1 times x raised to the 2 plus 1 power plus your c. Don't forget your c for an indefinite integral. There are always an infinite number of possibilities here. That's 1 over 3 times x to the third plus c. This expression has the integrand x squared as its derivative. Is that true? We'll check it. To check it, we're going to take the derivative of 1/3 x to the third power plus c. Take the derivative of that. You are going to get 1/3 times drop your exponent down, 3, x to the subtract 1 to get 2, plus 0. And sure enough, that's all going to reduce away, and you're left with just x squared, which is what we wanted. Does this work for negative exponents? Yes. Yes, it does. Let's try it to see that it does. So the integral of 1 over x to the negative third power would be 1 over, in this case, n is equal to negative 3 plus 1, x to the negative 3 plus 1 power, plus c is equal to 1 over negative 2 times x to the negative second power plus c. So the question is this expression, does that expression have derivative x to the negative third power? Let's try it. Let's check it over here. Negative 1/2 x to the negative 2 plus c. Take the derivative of that. Well, you got your negative 1/2 up front. Drop your negative 2 exponent down. Subtract 1 to get x to the negative third plus 0. And sure enough, the 2's reduce, and there's a negative there, and the negative. All of that reduces to just positive x to the third, which is what we wanted. So yeah, it works. With the notable exception, and you should add this, the power rule does not work for x is equal to negative 1. So, I'm sorry, n, the exponent, is not allowed to be negative 1. So, add that note in there, and we'll think that one through. Let's just think why. Why would the integral of x to the negative 1 not work? Okay, so that's really just 1 over x dx. But wait, what has the derivative of 1 over x? The natural logarithm. So we already know how to do that one. We don't need a rule for that one. And in fact, the power rule would give us the wrong answer there. So you have to exclude the case for the natural logarithm. Pow. A poorly formatted, pixelated picture and some alliterative words of a ton of integration formulas. And even some properties of integrals thrown into the mix there. But we're going to talk about the first few, but let's start with 3. What has derivative of 0? Integral of 0 is asking what has derivative of 0? Well, any constant number has a derivative of 0. So there's your plus c has derivative of 0. What has derivative of 1 for the fourth formula there? Well, remember, 1 doesn't have to be written, so we could just say the integral of dx, so integrate. Derivative of 1, well, x. Take the derivative of x, you get 1. Take the derivative of x, you get 1. Sure enough. Power rule we just covered, and they excluded n, negative 1. Well, what has the derivative of cosine? Sine does. What has the derivative of sine? Careful here. Negative cosine. All right. So if you have positive sine in here, what has derivative positive sine? Well, cosine primed has derivative negative sine. And so if you're looking for the derivative as sine, you need to take negative cosine and take its derivative for it to be the antiderivative there. Secant squared is the derivative of tangent. Cosecant cotangent is the derivative of negative cosecant. Again, careful with your signs there. Secant tangent is the derivative of secant. Cosecant squared, again, careful with your signs, negative cotangent. E to the x is the derivative of the parent function e to the x. And we're going to cover these a little bit more, but you know what? Let's take a look at a little bit. These don't pop off of the top of our head quite as much as usual, but the derivative of a to the x is ln of a times a to the x. Remember, ln of a is just a constant number here. So what has derivative of a to the x? Well, a to the x will give us a to the x. When we take the derivative of it, we'll get the a to the x that we want here. But we do not want that ln of a. So just like the power rule, we multiply by 1 over ln of a to get rid of it because it doesn't show up in our integrand, the thing that we're considering to be its derivative. What's the derivative? What has derivative 1 over x? ln of x does. Why the absolute values? Because here we're allowing negative numbers to be an x. There's nothing saying that that isn't okay. However, the domain of natural logarithm, because the logarithm is the inverse of e to the x, so natural logarithm ln of x has a domain which is only positive numbers. So we have to put the absolute value around there. And if you're astute, you'll notice I forgot that. However, it's important. Okay. Let's see, what do we got next? Okay, so let's verify an integration by taking the derivative of a family of antiderivatives there. So what we're going to do here is we're going to verify that this has derivative, this has derivative of that. So to do that, we will just take x squared over 2 plus e to the x plus c, and we'll take the derivative of it. X squared over 2 is 1/2 times drop down the exponent of 2 times x plus e to the x has derivative of e to the x plus 0, and sure enough, that equals to x plus e to the x. Check, it worked. Okay, let's verify this one. Again, the answer is the derivative. The answer has derivative. This is the derivative. Let's verify that. So we'll take the derivative of our result, the antiderivative, x times e raised to the x power minus e to the x plus c. Take the derivative of that. Okay, be careful here. We are going to need to do a power rule. FG, so derivative of the first guy is 1 times unchanged second guy, e to the x, plus unchanged first guy, x, times the derivative of the second guy, e to the x has derivative of e to the x, minus the derivative of e to the x is e to the x, plus your 0 for your c. All right, so that's that. And e to the x minus e to the x, that goes away, and sure enough, x e to the x. So check. This is the derivative of that expression. And in Calc 2, you'll learn how to actually do this integral. It is not an easy one at all. That's not an obvious one to see. Like the rest of these, we've kind of been able to think our way through, but that one's not obvious. Okay, let's do a few more examples here. Oh, the internet's lagging here. We'll stop and pick up a new one.